My name is Mohammed Al-Kafaji, and the title of my talk today is Leveraging Federated Machine Learning to Improve Intrusion Detection in IoT. And I have this little slide to just kind of introduce myself furthermore. Basically, I started my journey in academia in Liverpool, John Moores. I did my master and PhD there, and I worked as a researcher there for a couple of years, and then I moved to Reading. I worked there as a lecturer, and then I have been working with Reading, Huawei ICT Academy of Reading as an IoT instructor there, and I'm still kind of part-time there. But my main kind of position as a senior lecturer at the University of Lincoln, and my research is mostly on distributed systems, AI in network, like things related to data mining in network, intrusion detection. And if you need to learn more about my research, you can just scan this barcode and it will take you to my profile. So the outline of today's research is basically to discuss the IoT security landscape and then move into the concept of federated learning and why it's useful for IoT, and then a comparison between the traditional intrusion detection systems and the federated intrusion detection system, and the main component of federated learning then into some challenges and future directions. So this basically, as any research, started with an issue, which is here basically the security within the IoT network, then moved into idea, design, and some evaluation, which will be looking into what we have proposed as a federated learning model, and how we evaluated that in terms of accuracy as well as the other parameters such as time and performance. So before we kind of dig deep into the federated learning, I would like to kind of define what is the IoT network that I'm focusing on into my research. So the IoT, the Internet of Things, is the network of a physical object, which calls things here, that is basically capable to connect into a network and able to kind of exchange data over that network. So this could be any physical object, from being a sensor embedded in a wall, or it could be a smart appliances at home, or even it could be a weather station, or kind of a smart vacuum or a robotic vacuum that you can control over a network. So all those smart objects, they form what nowadays called smart home and smart cities and so on. So having this interconnected object means basically they exchange data over this network, and the massive amount of data that is exchanged over such network, it's become huge and requires some mining, and some of these data are sensitive and require some kind of secure communication and network. Otherwise, many decisions and automated system will be kind of vulnerable for attacks. And the kind of real-time map here is just representing a DDoS attacks where a botnet from a vulnerable kind of IoT devices, they form the cluster, and then they start to overwhelm the network or a specific server with lots of requests. And the idea here is just basically to get that server down or make it unavailable for a legitimate request to be processed by that server. And surprisingly, the growing of those devices, and due to some limitation with the capacity and etc. that we will look into the next slide, but getting that security industry of IoT is growing massively over the last few years, and currently is anticipated in 2025. The industry will worth around 30.9 billion US dollars in terms of the investment, whether of research or it's an industrial application or R&D kind of development for security systems to secure IoT network in smart home or smart cities. And this is basically the IoT network. I mean, it's mostly vulnerable due to several factors, and kind of the main thing is the heterogeneity of those devices. As I said before, it could be any object. It could be a sensor, it could be a mobile devices, it could be a small smart appliances at home. And this heterogeneity of devices and connected through any gateway or any mean of interconnected devices make them vulnerable in the way that hackers could basically intervene their communication through their Bluetooth, or if they use a specific communication protocol such as MQTT or whatever, they can intervene and then push some malicious data into that network that could influence any decisions could be made. Also, resource limitation of those devices make it very difficult to kind of implement things like encryption, decryption of the data, or implementing some AI model, for example, to try to filter the communication or the data that goes in and out of those devices. So that limited resources make it kind of only available for that device to function, to send data, but not to kind of deploy models or kind of security measures to secure that devices. Other limitation is basically the scalability. When we have a network of 100 devices, it's not similar to have a network of 100,000 of devices. So securing that network, it will be much more difficult. And some of the kind of common intrusion threat is the distributed denial of services with a DDoS attack, and botnet attacks, spoofing, and more or less they are kind of works in a similar way, where they try to find a vulnerability in a specific devices, and then they use that to access that device and then manipulate either the data that's generated or the data that is received by those devices. And the three main security vulnerability here is basically having the authentication and authorization basically for the network. So many IoT devices lack this robust authentication when it's come to connectivity, as I give the example before of connecting through Bluetooth or MQTT. So having all those devices interconnected into a network, most of the time you won't be stressing the way that they connect to the network or authorizing those devices. So, for example, nowadays when we try to log in into our university account, we use like third-party authentication through SMS or things like that. But that is not feasible with the IoT network. So when you connect things when you deploy sensors or when you deploy a smart object, you want them to be synced into a network and start to send data without any delay, and that authentication and handover between networks is not always possible. Lack of data encryption and decryption, so the data that get generated from the things is not always encrypted. So if we have a sensor that generates, if we have a temperature sensor in this room that is continuously monitoring the temperature in this room, it's not necessarily the data to be encrypted at the gateway before it gets sent to a specific server. So if a hacker would be able to access the data and they understand that basically the process of the use of this data is to be monitoring the temperature to put on or off the heating, then basically they can manipulate the data and then affecting or triggering some other surfaces or the heating to be on without the actual need for it. Insecure software and framework. So this is basically another kind of major issue because of the limitation of the devices, of the IoT devices in terms of memory or space. They are not capable to handle software with lots of security libraries that able to kind of measure or monitor the security aspect of those devices, but rather than just getting to do one aspect of it. And one of the kind of well-known security breaches in 2016, there was the Maria botnet attack, where there are hundreds of thousands of devices, basically the vulnerable devices of IoT. They managed to kind of, the attackers managed to get control of those vulnerable devices, and this is mostly in Mexico and a few other countries, and they were able to kind of target server for Amazon, Twitter, Netflix, Spotify, and PayPal, and get them down for a couple of, I can't remember the exact time, but it took the whole server and the services down, and this is purely just overwhelming the network with random requests and causing those services to go down. Some other examples, again in the VPN filter, and one of the popular thing is basically the Vergada camera, and this is kind of a startup company that sells security systems or monitoring systems, and they got them installed in schools, hospitals, and prisons. And some Swiss hacker, they managed to get into their server and obtaining all those feed from the live cameras from over 150,000 live cameras, and then basically this is could be used for different purposes, could be trained a machine learning model or something, and the main thing here is basically having a monitoring system installed in a school, and then hacker could be able to obtain all those data. This is a massive data breach in this sense. Tesla Model X hacked through their Bluetooth device by a cybersecurity expert, and basically make it also vulnerable in terms of using the wireless key system or the key entrance, and they managed to kind of instruct that Tesla to be on and off using a Raspberry Pi. So it's lots of scary examples, and normally to secure an IoT devices, they have to be into multiple layers where you can done series of authentication, and most of the time this would require you to have some direct connection to that IoT devices, and what they start to use to do is basically to have a SIM card installed into those IoT devices to allow them to get a direct communication with those IoT devices, but it's rarely to be the case that you will have an IoT devices that you were connected through the internet directly through a SIM card or a direct mean of communication, and this is basically due to expenses of those IoT devices. It could be due to kind of a requirement that could prevent you from connecting directly into those devices. But then to secure those devices, you'll have the intrusion detection system that could be installed on a switch through that network. So basically you'll have a network of IoT devices, and then at some point those data will be transmitted through a switch, and then on that switch you can install that intrusion detection system. And that intrusion detection system, it's mainly to monitor the traffic and try to assist with identifying any vulnerability or risk, and hopefully to block attackers or devices that try to intervene or send a data that could be misleading or malicious within that network. However, the main issue with the traditional intrusion detection system is that they are trained into a centralized server. And to train them into a centralized server, they will rely on the data that is collected from IoT devices, and that's not always possible to get all those data into that centralized devices and to train them. And by the time that you train a new, let's say accurate model to detect intrusions, they will be inefficient against unknown attacks. So because attackers, they keep changing their behavior within the network, so by the time you get a robust model, you will be basically facing a new attacks that not being introduced into that new model. So they are inefficient, they are always behind, and they require lots of data to be trained and kind of deployed. And the other limitation is within the IoT is to have that resource restrictions. And that resource restriction could be memory that won't be able to handle running such a machine learning model, or it could be issue with the connectivity to the centralized model. And from that where research start to develop, and then we have start to seeing things like TinyML. And TinyML itself is basically, it's a machine learning model, but they try to manipulate the parameters within the development process to try to shrink the size of the model of the machine learning to be deployable on on devices with a limited capacity. But this comes on effect on the performance of those models. So trying to manipulate the attribute or the parameters that you use to train them is basically losing some data or kind of useful information to build that model, and hence affecting the performance. So the emerge of collaborative intrusion detections come into the place where things became more kind of under the use of distributed servers, and the knowledge that is deployed or implemented by different servers to come together to tackle a specific attacks. And the main idea here is basically if you have multiple host machines, and they have to implement different kind of machine learning algorithms to tackle different type of attacks, and then at some point you will have a central node or a central server that combine all this knowledge, and then apply a master model that could predict or classify a specific traffic into being a malicious or a benign traffic. The issue with this collaborative machine learning there is a limitation to the privacy and security of the data. So it's, again, if you need to consider a scenario where healthcare, for example. So normally patient data cannot be shared across different entity or organization. So if you build a machine learning model into one kind of institute, is possible to share that knowledge out of those data, but not the data itself to be transferred into another institute. So the privacy of the data, sharing sensitive data, became an issue across different devices. The scalability, basically managing that growing number of IoT devices that could be connected to multiple distributed system, can affect one kind of local area due to the number of devices. So if you think about it, for example, like city center, and then at the edge of the city center. At the city center, there could be more IoT devices connected to the network, but then at the edge, there are less. So if you have two distributed intrusion detection systems, then one could be more overloaded with a request, and then the other one, it could be more idle. So the scalability at one place could be an issue if we need to have that collaborative AI or collaborative classification. The other issue that could be also shared with the federated learning is the trust issue. So if you have one model implemented at one server, so how would you trust that server or that system if you have received the traffic by another system? So there's a trust between collaborator. It also need to be built upfront based on specific parameters and need to be defined in advance. So as a solution for all this centralized training or collaborative machine learning, then now there is an interest into a new field of developing intrusion detection system using federated learning. And what federated learning is, it's basically a decentralized machine learning that has been introduced by Google in 2016. And the main idea of this is that no data shared from the devices, but rather the knowledge gets shared. So each local device will train its own model, and then only the knowledge or the trained model will be shared with a central server, and based on that you will build a global model that later will be sent back to those devices. So the central server will do all that aggregate, and they do the aggregation through performing the algorithm of federated averaging. And that federated averaging is simply an averaging algorithm that take the weight from each of the developed model and then build the over, which we'll discuss in the next slide, I think. But just to explain the workflow of federated learning. So the federated learning is started by having the data that is sent from the IoT devices into each of the nodes. And the worker node here, it could be a gateway, it could be an edge device, it could be a router that is basically have some microcontroller or micro processor that able to do some machine learning or implement some machine learning algorithms on a smaller scale, and then those devices will use the data that is sent from the any IoT object to train a model, and this model will then send the kind of output parameter through the dictionary into a central server, and on that central server you will have the aggregator model, which is the Fed averaging that mentioned in the previous slide, to build the master model. And the component of this federated intrusion detection is basically the data that it's generated from those IoT devices to log all the traffic data. And the local training model, this is normally a lightweight algorithm such as SVM. The autoencoder is mentioned here as an anomaly detection algorithm, but it's not really applied to the lightweight. But this is again mentioned here because the edge device or the worker node that is used to train the federated learning can be different from one scenario to the other. For example, if we are working, if we are considering a scenario of a smart home, and then you have multiple gateway into your home to deploy as a federated learning, is completely different than having an edge devices into an industrial network and industrial IoT devices where you have edge computing that is much more powerful than your edge at home or your router. So again, it depends on the capacity of the edge devices that you have. Then the lightweight algorithm here could be SVM or could be autoencoder, that is a deep learning algorithms. The technique like federated learning, averaging, this is more of research interest, and here where the optimization is taking place nowadays. So the machine learning algorithms, there is no much of kind of let's say novelty in there. So whatever machine learning algorithm that work into that area, you can deploy it into that worker node. But the optimization is done through the federated averaging into that central server. So within that central server, you will be receiving models or pre-trained models from a different working nodes. And the kind of the master model will be built based on those data that received from those worker node. So how would you calculate or how would you treat these data? It's the main question here. Would you take the average from all nodes? Would you give a specific weight for a specific edge devices or a specific worker node? Again, that's purely based on the data set that you have and the distribution of the data. And if we are in a real world, then the question here, which worker node would you trust over the other worker node? And the fourth basically component, which is the global model, and after you basically calculate all those weightings from those different worker nodes and you build one overall master node, you would need to push back this into those worker node to be used for classification for the upcoming traffic into those IoT devices. Now, the federated learning have several types. There's vertical federated learning, horizontal federated learning, and the transfer or federated transfer learning. The main differences between those is the feature space. So the horizontal federated learning is mostly used when you have the same feature space but you have different sample size. The vertical is the opposite, is you have a different feature space but the same sample size. And if I would simplify this, if you look at training a model on a one worker node where you are targeting one class, so when I say one class here, I mean a predicting class in machine learning. For example, if we have a security, an anomaly detection algorithm, and then you need to do multi-classifier of DDoS or spoofing attack or whatever. So those are multi-class. So if you need to focus on multi-class classification, and in that case it's horizontal, so you give a specific features for a specific working node to be able to predict a specific class. In the vertical federation, where you basically predict the same class, so all of them, they are focusing on one class, which is the DDoS, and then in that case, you just distribute the sample space and the feature among the working nodes. The federated transfer learning is kind of mix and match of both. So you would be using the feature space and the sample space, because both are different, and allow them to kind of implement in each local worker node and then deploy into the main master node. So in that area, we have kind of tried to build an anomaly detection system, mainly focusing on DDoS attacks, and we have used a data set from the Canadian Institute of Cybersecurity, which is basically a good enough data set. It's around 13 gigabytes of size, and it contains traffic from different IoT devices. Some of them is malicious, and some of them is just a benign network or request. The thing is, with this data set, it got multiple classes, but we only focused on the DDoS attacks. And the local model training, which means basically the worker node, they have been basically configured with using SVM, support vector machine, and focusing on one class, a classification SVM. And the reason that we have used SVM, because of the time complexity. So the time complexity of SVM, it's make it more suitable to be implemented in IoT devices, and the time complexity of this is n multiplied by d, which n is the number of training samples and d is the number of features. And the federated averaging is the method that we have used. Again, in terms of the academic settings, most of the optimization is done at this step, but our initial research just purely kind of treated all the worker node with the same weight, and we have used the federated averaging to build the master model. And for the development part, we used Flower framework, and the Flower framework is basically allow you to manage all that communication between the different working nodes. So as I said before, we have multiple IoT devices. Now those IoT devices, you can think of them as Raspberry Pis. Okay, so you have multiple IoT devices, let's say multiple micro controllers, multiple of them, and then you have one kind of master server that aggregate all the model from the different IoT devices. So those IoT devices has been configured with SVM, support vector machine. And the Flower framework in this scenario allow us to kind of control that communication between how many IoT devices that we need to set. In our experiment, we tried with 1, 3, 5, and 10. So when you configure 10 IoT devices, you need some mean of communication that collect all those data that get trained on the initial data into the master server, and then build a global model, send that global model back into those nodes, and then learn from the upcoming iteration and data into those devices. So that communication back and forth between the master node and the devices is all managed by the Flower framework. So now, in terms of results, we try to kind of measure the result with and without federated learning. So having federated versus non-federated learning, it was our initial experiment, and as you can see, that is the SVM on a central node without having any worker node. It achieved quite high accuracy. But then when you use federated kind of learning, now SVM with a 3 node, SVM with 5, and SVM with 10, you can see the accuracy start to drop, and this is quite expected. So with the federated learning, we are not expecting to improve the accuracy, but it has different objective, which is basically the workload management of those devices. So in terms of time, it will achieve less time, but still the accuracy in acceptable bands. So if we look at the differences between the 10 worker node and the SVM with a master node, it's not a huge difference. And as you can see that the kind of a precision and recall and the F-score maintain more or less closer kind of output. The main idea here, or the main reason that the accuracy drops when you use federated learning, is because the data is fractured or distributed between those nodes, and make it less kind of the model themselves less knowledgeable of all other data that is available with the other node. Even with the global model, that is aggregate all those model from a different working node, that still make it less kind of accurate when we build or implement all those knowledge or machine learning into one central server. However, when it's come to kind of checking the accuracy with other machine learning algorithms, such as the isolation forest, the random forest, and artificial neural network, SVM it's fit on the top of the range with kind of similar output to ANN. However, with ANN, you will get kind of different physical matrix and output in terms of time and memory. So in terms of time, it's kind of the delay wise for ANN is higher than SVM. So if you look at the SVM with a 10 worker node and the ANN with 5 worker nodes, the achieve of training is 27 seconds compared to the ANN, which is 41 seconds. And this is lead us to kind of a conclusion here, where having more worker nodes and achieving reasonably low latency make it more suitable for deployment in IoT devices. And also, if we compare the memory usage for SVM is quite high, unfortunately, and this is because the SVM it's a linear algorithm compared to ANN, which is just a black box that we cannot actually interpret the result of it. So if we need to kind of conclude this research, if we compare the two or the two accurate algorithm here, the SVM and ANN, so in comparison, the main attribute that is necessary for implementation in IoT, so the interoperability for security, so this is more integratable, so you may expect what SVM could predict based on the data that fed into the model. However, with ANN is often a black box and you won't be able to interpret their output. So in that case, you may think whether ANN it would be suitable to predict a security or a threat or a vulnerability in a device when it is basically unpredicted in the way that is function or perform. Also, in terms of IoT, you would need to focus on lightweight and fast prediction. And in that case, you would need to look at the models that can run and generate a prediction with the lowest latency. And SVM here it has performed well with the lowest latency compared to ANN and random forest and the other algorithms. So the last comment here on federated learning, although it is kind of accurate and more manageable for IoT devices to have multiple kind of node and then those nodes fed into a central server and then have an aggregator, there is a potential issue of backdoor attack. And this backdoor attack is mainly initiated by a node that could be hacked into that system and then fed that local worker node with the data that could mislead the development of model on a one node, and on that basis it will affect the global model as well. So an example of this is data label. So imagine if there is a malicious node or a vulnerable node that could be hacked, and based on that you could basically change the data or the kind of inputting data to that model. For example, if the speed limit is 30 and then you can manipulate the data that entered into the model to be 80, and in that case you will be manipulating the training data in one local mode, worker node, and then when you push this data into a master server, it will affect the overall master model. So this is kind of an issue with the federated learning that is currently under research, and that basically lead us to kind of the challenges into the federated learning, despite their benefit being lightweight, in terms of scalability, in terms of time sensitivity to generate a prediction, but there is a risk of data poisoning that could be pushed from a node or a hacked node within the system, and this basically could also contribute to communication overhead and device constraint as well, ensure the capability with low power devices when it's come to train those IoT devices. So future direction, there is kind of a hot topic is the federated reinforcement learning. So those local worker devices that contribute to the building of the master node, they will be rewarded for the model that they generate when it comes to predict or classify a network anomaly or identifying a specific attack. So if they get rewarded, they get more weight, and that affected the federated averaging that I mentioned before. So instead of having the federated average for all worker nodes the same, then you will be basically implementing that feature of giving certain weight based on a certain credit that those worker nodes get when they predict or classify a specific network. And obviously lightweight model that is it's a need, is always there is a need to be a lightweight, and most of the machine learning models nowadays is not really a lightweight to work on an IoT devices that has a battery to keep them running for 10 years, and then you need to have that AI model with that power requirement, low power requirement. So yeah, federated reinforcement learning and lightweight model, it's kind of two key areas in this IoT intrusion detection systems. So thank you very much. I hope this has been informative, and happy to answer any questions you may have.
Hi guys, it's very, very interesting, I thought. Start off with the reality of cyber attacks, even in your car.
The models that you mentioned, I'm assuming that they're all essentially neural networks.
Yes and no, but some of them, they are predictable in the way they work.
Okay, but to train the network, then you're training it on the messages that are transferred between the various, the server and the IoT device. And so therefore, those messages that you're using for training, someone will have had to have said, this is a valid message, and this one is an invalid message. So there's lots of human interaction to actually classify the messages, the data that's being used to train. Is that right?
So not really. So the master node, this is the aggregator, it won't have any kind of messages or data transferred between them.
No, I'm talking about
the worker nodes.
The worker nodes.
Okay, so the worker nodes, they will collect the data from the IoT devices. So it's an automated process. There is no human.
Well, how do you determine whether it's a valid message or an invalid message?
Oh, okay. So those training, this worker node will be initiated with a pre-trained model from the main server. So, for example, if we are developing a DDoS in this work, for example, in our model, so to start with, those IoT devices, they have pre-trained with the model, or they have been deployed with a pre-trained model that detects DDoS, but is not very effective. It's just as a starting point, it's cool-off start, and then based on that model, you will be developing the model locally, and then update the main master node parameters based on the new data within those local nodes, if that makes sense.
Well, I'm still not clear as to how the IoT device
Yes.
knows whether the data that it's looking at and is adding to the model is correct or not.
So the data that is received from the traffic is not assist at this point. Everything is fed into the learning. And then later, that model will be penalized for having correct data or incorrect data. So at this stage, that's why I said the that type of attack that could be maliciousing these devices, sending the data that the node, they treat it as a legitimate data, traffic data, and they deal with it as data to learn from, but they are actually malicious. So that's the type of attacks that I mentioned in here. It's called backdoor attack. So if we say there is no attack, then every data will contribute to the learning. And if you are concerning about the classification, whether it's attack or not attack, I mentioned before that we are using one class SVM, which means every traffic data in that learning process is treated as a legitimate non-attack. Anything that is different to those initial attributes, they will be considered as attack.
Right.
If that makes sense.
Yeah.
All right. Yes.
So, okay, thanks. So, on the centralized model, who hosts that?
On the centralized
Yeah,
node.
because you showed the local the local models potentially being hosted on, say, the home gateway, like on the Wi-Fi router, because that's the only thing really that has potentially enough power to do that in a home. But who's hosting? This is exchanging information it's learned with this centralized model. Who owns that centralized model, and how do they?
So, are you asking in general or in a specific scenario?
Well, in general, because normally the only single point of contact you have is with, say the BMG or something that's run by the service provider.
True.
But they won't be doing
They won't
do
yes.
that. So
if I give an example, basically federated learning in this context is being applied into intrusion detection. So in that case, any service provider, they would be willing to have that kind of master aggregator installed into their network, and every gateway that interacts with the IoT devices will be their worker nodes. So the network provider will be the hosting of this master node. But if we talk into another context, for example, federated learning in healthcare. So this is again is another big area where basically if you have to predict, for example, skin cancer, and then you have in one hospital 100 patients, in another hospital 300 patients, and then none of those hospitals is willing to share the data of their patients. So what happens in that case is that each hospital, they have their own model, and then instead of sharing the data, they share the model. And then again, there is aggregator, and then based on kind of agreement between those two hospitals where those aggregator will sit, and let's say this is third-party healthcare organization that collect the machine learning model that is being developed in hospital 1 and hospital 2, and then do whatever federated averaging or whatever to build that global model and then distribute it back to those hospitals, which hopefully will be more accurate because it has more number of patients in that global model.
Yeah, that kind of enterprise model sounds a bit more practical because you've got total control of, it's one domain essentially, and you've got total control over the whole network.
Yeah.
In a public, like if you've got all these different ISPs and different people getting their services from different ISPs with different types of gateways, some can do this, some can't.
Yeah.
It's much more limited.
Yeah, but this is if you apply it into a specific industry by a specific kind of a provider. For example, I mentioned the camera surveillance company where they have their own cameras installed in hospital and schools. So, for example, they can treat all those different cameras in different places as their worker node, and as a provider for the service, they have their global model.
Yeah.
The question of intrusion detection you've got up there, but coupling it to the local models, you had a system which had 3 local models. Well, that's the minimum number you can have to have an error correction or an error detection of, one, if 2 are okay and 1 isn't, that's okay. Now, surely going to 5 is a safer system, but going to 5, from what you said, does that mean that the data becomes fragmented because they're lightweight systems, so you can't get all the data sets out to all the local models?
So basically the number in our experiment we tried with 3, 5, and 10. This is also a research question, like how many worker nodes do you want to have based on the data set that you will be given. So it's not necessarily to be 3 or 5, it could be 50, but this is, again, as you said, the fragmentation of the data and the capacity of the worker node themselves that comes into the place, and the question is whether they are capable to process data in a scale of megabytes or gigabytes, and the communication with those nodes to kind of get all the attribute. So in that scenario here, 3 and 5 and 10, it's the accuracy between them is not huge. Like you can see, like with SVM with a 10 node is 97.3, but with a 3 node is 98. So again, that's because it's fragmented the data across 10 devices. It's become less accurate. But if you look at the time to generate this prediction, it's much less than using only 3 nodes, or even if it is have it all in one global server.
Yeah. Thank you.
Nice.
For example, if you have, how long does it take to train an AI? For example, if you have 5 nodes, that's one. And the second one is, I've heard that we have exhausted the AI, have exhausted already the data, in the internet, and now they're resulting to the synthetic AI. What do you know? Can you expand about the synthetic AI?
Sorry, the second question, just repeat the second question.
I've heard that they have expanded, they have, exhausted.
Exhausted.
Yes, all the information in the internet, the AI. So now they are resulting to synthetic data to feed the AI, to train the AI.
Yeah.
So do you know about that? And what is synthetic data, basically?
Synthetic data, yes. I think this term is more applied to a specific field of maybe in healthcare, or maybe is there, I don't know, in traffic monitoring and traffic classification. I haven't heard this term much, but back to your first question, like the time. I would say the time is much vary from one experiment to the other, depending on the actual worker node spec or specification. So in our scenario, we have used a cloud-based server, and then we implemented the Flower framework. And then the worker node, they have, I think, roughly 1 gigabyte in terms of RAM, and I can't remember the CPU, but in terms of the 13 gigabyte divided, basically some of those data are excluded because they are not DDoS, and we focus on DDoS only. It took half an hour for each worker nodes, and then the global model to be generated by the master node, it just take a couple of minutes, because it just calculate the averaging between the nodes. But obviously, if you have a bigger capacity on those worker nodes, then you will shrink the time if we are doing it with the same experiment. But if you have larger data, then obviously you may look at more data. That's the SVM. It's quite straightforward in terms of time complexity. So the more data is going to scale linearly with the data size.
So just a follow-up, if you have the same IoT devices, for example, and then you're going to implement them to another place, can you use the information that data gathered to another set of IoT, but they are the same?
Yes, that's the kind of aim for this data set that generated by the Canadian Institute of Cybersecurity. So they are generating a real IoT traffic with DDoS and different type of attacks. And the idea here is that when you train a model that is able to predict anomalies, is to have it implemented in a real world environment or a network to be able to classify traffic.
Okay, thank you.
Thank you.
Mike?
A different question.
Yes.
The question of cyber security. I noted earlier that you had some connection with Huawei.
Yes.
And it's always puzzled me as to the large network which for doorbell cameras. Now that is accessible. I don't mind the local police accessing. I haven't got a doorbell camera, but if I had one, I wouldn't mind them accessing it. But I would object very much to China, the secret police in China, accessing my doorbell camera. So what's the question on the security of that kind of network? Because it must relate to what you are saying, the Internet of Things. I know it's not the Internet of Things, but it is a network.
Well, this is a difficult question. I think it's politics involved in here, but in my role, I'm just an IoT instructor, so I don't know whether actually they do have access to those doorbell cameras and so on. But the research that I do, it's mostly local area network. For example, industrial IoTs. And then industrial IoT, normally you'll have more controlled environment in terms of connectivities, but the vulnerabilities happen through the communication protocols within that local environment. So if someone got access into a device through a Bluetooth connectivity, or within that local network you get into that channel of any publish subscribe kind of protocol, such as MQTT or anything, and then you start to send malicious data within that network. So the research is mostly focusing within a controlled network. Then the internet in general is basically uncontrolled, I would say, and normally the power is for whoever is strongest within that game, you know. So it could be the US having access to your data, it could be China, it could be whoever have basically that power. So I won't be able to comment much on this, but I think we need all to be disconnected in certain areas to be more protected.
Yes, I think that's a very good question, a very good answer to a very unfair question.
Thank you.
Over there.
Compared to language learning models, does federated learning have any difficulties with contextualizing data? So, for example, with the aggregator.
With what?
Does federated learning have issues with contextualizing data,
yes,
say, compared to something like language learning models?
Yes, so that basically dividing the data between working node always expose that federated learning model to have issues with basically some of the data could be biased in one node and then affecting the global model in a way that get overfitting or underfitting in some way. So this is always an issue, and I would say something here that federated learning, it's just a workflow to collect and to build a global model. So whatever the normal machine learning development process may severe from issues with development itself or with the pre-processing, it will still be valid with the federated learning. And the federated learning, I would say, it's just a tool that allow you to distribute the processing and then calculate it into one global model. And now if you are wondering what is the difference between federated learning and distributed learning, I would say the objective here is different. So in distributed learning, you will have the data into the master server, and then you distribute this data into the worker node, which is that distributed processing to utilize the CPU of those devices and collect the data. And federated learning is the other way around. Those worker nodes have access to the data and they don't want to share it with the main master node, so they do the training locally and then only they update the master node. So that's the main difference between distributed and federated. There could be another difference here. It's basically the heterogeneity of those devices. Normally with distributed systems, you have same set of worker nodes, but with the federated learning, it could be any any device hooked into that cluster and then start to feed data feed the global model with some learning. I hope that answered your question.
Yeah.
Yes.
So if say the DDoS attack is so there was quite a well publicised one last year where there was a vulnerability in TP-Link routers that attacked Microsoft. So if you had a high proportion of those and you were running the local models on those routers, which was kind of like you showed earlier on, would you be able to detect that, or would that be under the essentially deleted data?
In theory, yes. Basically, if you train that model on a similar kind of a traffic pattern, then you would be able to detect them. But in reality, again, attackers, they might change the behavior of attack or the network parameters. Then you may end up needing to tweak that model, and that's basically the idea of federated learning, is keep learning from the new traffic that fed into those worker nodes. Yeah.
I think that's quite interesting. So moving on to this, you're leading on with the idea of federated machine learning as a paradigm,
Yes.
where you use less processing, but they do their own building of the model and then send the model on without sending the data set. So
Exactly.
it's an interesting research area, I think, but it has problems, which is also identified, that you could have malicious attacks to that, and that's what you've been working on, isn't it?
Exactly.
In your
Yes.
standards and things like
Future work.
this. So it's early days yet, but let's see what happens. It's like, yeah, I think this is very, very interesting indeed. Are there any other questions before I talk about the next lecture? If I may take your
Yes.
HDMI lead. The next lecture